Awesome. So maybe we would get started. Thank you all very much for joining and for your interest in this week's Gosset Circuit session. My name is Kristan Temme. I'm a researcher on quantum computing here at IBM Research, and it's my pleasure today to introduce the two guests that we have today. And both guests have among other things, have a very strong background in quantum algorithms and especially in quantum computational complexity theory, which makes them the ideal guests for this week's topic. And the person just about next to me, that is Aram Harrow. Aram Harrow is an associate professor of physics at the Massachusetts Institute of Technology in the Center for Theoretical Physics. To give you some background, he has an undergrad and graduate degree, both from MIT. He's worked as a lecturer in Bristol in computer science and math, then went on to University of Washington to be a research professor, and now essentially has joined MIT as a faculty member. Interesting, if you're sort of active in the quantum community online, he's actually a maintainer of something called that SciRate, where people can rate articles and papers, and he's actually contributed to the blog that's called the Quantum Pontiff. One further down, we have David Gosset. David Gosset is also an associate professor at the Department of Combinatorics and Optimization at the Institute of Quantum Computing at the University of Waterloo. David has a PhD from MIT and then went on to do a postdoc at IQC, as well as a postdoc at Caltech. And he actually worked at IBM for some time before joining University of Waterloo as a professor. So just to give you some background on what we're doing now. So what we're trying to shoot for right now is sort of like a virtual panel or a question and answer session that we're going for. And so you can think of this as maybe a little bit like a podcast. And we're trying to generate an interesting discussion that's hopefully lively enough and instructive. Maybe as a heads up, at some point in the discussion, Aram will have to get up and leave for a couple of minutes, but then will rejoin us later. So we're really grateful that he could join us, because in these times it's difficult to get your schedule worked out, because that's very tricky. And so we're going to be able to get to, at some point, we're going to be able to get to the questions that you can ask and in the chat window. In that context, we'd like to ask you for a favor. So if you state questions, would you be able to sort of provide a little bit of context? Because the questions tend to flow pretty quickly. And then we basically have to backtrack and figure out what you were asking. It's going to be very difficult. So a little bit of context in which that question was asked would be helpful. And in the end, actually, when the discussion is over, we actually plan to post a couple of links that we're going to refer, a couple of references above in the links, so that we're going to refer to. So to get into the topic, since we went through all the formalities, today's topic has been titled "Not All Circuits Are Created Equal." And what that means is basically you may have already had some experience with quantum circuits, both professionally or through the through this circuit session. And what you're going to realize is basically, well, some circuits are more valuable in some sense than others. And the valuable circuits, to some extent, or the interesting, better said, circuits tend to be circuits that are referred to as being hard. And what we're going to do in this session is essentially discuss what that actually means, and which is going to be something that's going to take us down a road that is inevitably going to end up in computational complexity theory. And we're going to have a discussion about that, what that means. And in that context, it's important to know complexity results are typically results that are asymptotic scaling results, and we'll just talk about that and how that pertains to things with finite resources and so forth, especially in the context where we are right now, because right now we're entering a phase where larger and larger quantum devices are being built that are well controllable, and they are becoming increasingly more difficult to actually simulate on a classical computer. So this is, we're going to dive into what that actually means. So let me start out with the first question. As I said before, so we talk about hard circuits, and so that's just a general statement, but what does that actually mean? So maybe let's start with Aram right next to me. Could you explain what people mean when they talk about what hard circuits are, or whether that question itself makes sense to that end?
Sure. Hi, I should say hi, David and Kristan. Kristan, thanks for inviting me to this. Thanks, Evan, for tuning in, or whatever it's called on the internet. So I guess hard can mean a few different things. There's sort of the common sense notion of hard, which is it's too hard to do it on your computer, right? And then there's the complexity theory version of hard, where you try to make that a little bit rigorous. And those are partly aligned, but not totally aligned. So for quantum mechanics, for example, it's hard to computationally estimate the mass of the proton. That's a hard problem from quantum mechanics, if you want to do it from first principles. But the complexity theorists would say that's hard in the sense like it's hard to figure out if white has a winning move in chess, as in we don't know how to do it. It's very hard for our computers. It seems to run into exponential problems. But in principle, there is an answer, and there exists a circuit that would just write down that answer, printf, yes, white has a winning move. And that would not be, there's sort of a trivial, uninteresting answer. So I would say, back to the quantum question, even a specific quantum circuit, probably we don't know how to simulate the output of that on a classical computer just by looking at the quantum circuit and doing something from that. There might be some sort of cheating shortcut, but even individual circuits seem to be hard. When you try to formalize that, you have to talk about families of circuits. So you might say, in general, circuits with 100 qubits and 1,000 gates, we don't have a simulator that works for all of those circuits. And that's sort of how we can formalize it if we want to try to make rigorous statements. And that's useful it's certainly useful to be able to say rigorous things, but it forces us to be a little bit more conservative than just saying, than what we know from our common sense notion, which is that even a single circuit can be hard to simulate.
Yeah, maybe if I can just build on that. So, as Aram mentioned, we talk about families of circuits, and the sort of complexity theorists' way of saying that something is hard is to say that the time or resources required to simulate it as a function of the size of the instance or the problem must, grow more quickly on a classical computer than just running the quantum circuit. So the resources on the classical computer grow more quickly with the size. But then, of course, as Aram mentioned, in the real world or with a real device, we just have a limit on the size because the devices now are small, and so there's just a few circuits that we run. And so then, the challenge is understanding whether or not, we are in a regime where we're seeing the improvement from the asymptotic speed up that we know should exist, and whether or not that can be realized with the devices. And there's of course more challenges having to do with the fact that many of the speedups that we know of just can't be run on near-term devices. That we have to understand, whether or not there can be speedups in more restricted scenarios.
So can I ask in that follow? So you're talking about asymptotics, and that would probably mean scaling. Could you explain briefly when you would say something asymptotically scales hard, or something scales easy asymptotically, or when would you say something becomes challenging, or for a classical computer, in the terms of scaling?
Myself, well, I think there's a so I think the safest bet is when you have an exponential separation between the classical and the quantum computer. So in other words, the quantum computer has a certain let's say polynomial scaling with the input size. So for example, it might be linear, or maybe the square of the size of the input. And then the quantum computer would require an amount of time, which is say 2 to the input size, or something of that nature. So that would be an exponential speed up, and that would be one of the most dramatic types of speed ups, and the kind of speed up that you could really see at a small number of qubits. But on the other hand, like we have other examples of quantum speedups which are less dramatic, but that in some cases might be more well suited to actually running on near-term devices. So I think it's not a clear-cut answer in my view. What is the most? Yeah.
So then as a follow-up question, naturally, so why, I mean, why even ask that question, or why would we care about the fact that a given quantum circuit is hard? Is that relevant in any regards to if you care about an application or something, say, Aram?
Yeah, I guess there are a few reasons to care. I mean, it's a little bit like, you know, do I care that my laptop can compute this, do this ray tracing benchmarking quickly or not? And at one level, it's a benchmark. So we want to know, you know, this quantum processor that we just built, how capable is it of doing useful tasks? And before we get to useful tasks, we just want maybe a clear benchmark, just as a way to measure it, not useful in and of itself, but good to calibrate our understanding. And a really important calibration is relative to classical computers, right? Classical computers are a very mature technology and work very well. And the default state of quantum computers is they're not more powerful than my cell phone. So it's really useful to know when they get beyond that point, so that they because it's, in that sense, it's sort of a precondition for doing useful things. You know, ultimately we want useful things, but a precondition for that is that whatever the quantum computer is doing can't be very cheaply simulated by classical hardware. So that, I think, is one of the main reasons why it's useful. And whenever we have quantum speed up, we should always be kind of kicking the tires and saying, is it really a speed up? Maybe if we thought a little bit harder about classical algorithms, we could achieve it there. So I think even as we're doing useful things, we still have to go back and check whether they could also be achieved with classical hardware.
So David, would you say that question is particularly relevant to quantum computers, or is there some other? So why would you particularly care in the quantum setting of something as hard as opposed to maybe classically hard or something?
Yeah, well, I completely buy into this idea of kicking the tires. I mean, I think that quantum computers are they're a model of, the reason we're excited about them is that they're a model of computing that goes beyond the Turing machine, which was developed in 1936 by Alan Turing, and where everything we've done so far in classical computing is in some way, from a complexity theory point of view, equivalent to that. And quantum computers, move us outside of that. And so that's why there's so much excitement and so much potential. But when you build one of these things, of course, there's a huge investment and a great deal of effort from a lot of people. And so you want to know whether or not you really, how far along you really are, and whether or not you're beating the classical computers, because that's kind of, in a way, the whole point. So I think it is, this question didn't come up when classical computers were invented, because there wasn't a previous model of computing that was very popular and successful. But here we have a higher bar.
I see. So can you, for instance, give some what kinds of circuit you would say are actually hard to on a quantum computer, or hard to simulate on a quantum computer? Do you have something in mind there?
Absolutely. So I think there's, obviously, like, universal quantum circuits are the model of computing that we work with, and so like a completely general quantum circuit is hard to simulate. But one of the really fascinating things that has come from the study of this area is the sort of restricted models of quantum computing that are also hard to simulate classically, or for which we have evidence for that statement. And so those restricted models are things like constant depth quantum circuits. So the depth of a circuit is the number of time steps when you allow parallel execution of gates within a time step. So for example, if I had like 4 qubits, and I executed a gate on qubits 1 and 2 and on 3 and 4, those gates don't overlap. They don't touch the same qubits, so I can apply them at the same time. And so if I allow myself the ability to apply gates at the same time when they don't touch the same qubits, then and then I execute a certain number of steps, the number of steps is called the depth of the circuit. And so constant depth quantum circuits are, what you can do in a constant number of time steps, allowing for parallelism. And there's strong evidence that those circuits cannot be simulated classically. going back to pioneering work of Tirhal and DiVincenzo from 2002. And this line of work really has also led to many other restricted models, including instantaneous quantum polynomial time, the IQP model, composed of gates that are all commute with one another. And nevertheless, one can show that there's strong evidence that, again, you can't simulate those circuits. Likewise, there's these circuits that come from the quantum approximate optimization algorithm, and there's several other circuit families. And for all of these, we have some kind of evidence that you cannot simulate the output distribution, sampling from the output distribution of the quantum circuit. And so the excitement around those is primarily because they're restricted models, and they're a little bit closer to what you might hope to do with, the limited kind of devices that we have today.
I see. So on the flip side, so you say, okay, maybe you gave us some examples that where things are hard, but so Aram, would you say there's a case where you could immediately say, well, no, that's easy. We could immediately do that on a classical computer or something, or is there something you haven't? So is
Sure.
there some case where they?
Yeah, I mean there are a number of special cases where quantum computing can be, what quantum computers do is can be easy to simulate. And it's a very interesting branch of the field to try to figure out what they encompass. Because it gets at this question of, which is both a practical and kind of a philosophical one about quantum mechanics, which is, what is it about quantum mechanics that makes it so computationally powerful? One answer to this has been entanglement. And you can see that this is a feature of, so I guess I should say, what I mean by this is we know that if your quantum circuit never builds up very much entanglement, then it can be easily simulated by a classical computer. There's a few little asterisks there, but more or less that's true. And so this has led people to say that the nature of the universe is different, it's sort of a different computational model than the standard Turing machine model because of entanglement. And the nature of information is different, information processing is all different because of entanglement. And this is so I think it's interesting both for practical reasons and also to understand the nature of quantum mechanics and what it says about information in the world. On the other hand, there are circuits that are very entangled that are also easy to simulate. There are these Clifford circuits, match gate circuits. In some cases, the types of circuits that you get in adiabatic evolution can be easy to simulate because they have a lot of entanglement, but because all of the parts of the wave function have the same sign, they don't exhibit interference in the same way that you would expect. So there's this sort of list of cases that include, but are not limited to, lightly entangled quantum evolutions where we can simulate it. And so far, it seems that these each just carve out a small part of the space of possible quantum circuits. So it seems that sort of general quantum circuits still seem hard to simulate. And in general, the situation is a little bit like with classical algorithms. So if you say, what can we do with algorithms? You say, well, sometimes problems are convex. There are no local minima. You can just sort of gradient descent to the solution. Sometimes problems have this kind of dynamic programming structure where basically they involve doing something on a line or doing something on the tree, and they're easy for that reason. And you can view those as limited exceptions to the general rule that the default is that things are very hard. Right? If I just tell you like a random function, a random problem, it's probably going to be very hard unless it just happens to have one of these structures that us humans with our puny brains have been able to grapple with. And similarly with quantum circuits, like the default is that they're all hard, and there's a limited number of exceptions. And for the ones outside of it, we have some ability to use complexity theory arguments to say why they should be hard. But even there, to some extent, we're just saying they don't lie within our limited set of easy cases. And that's, that forms a big part of our evidence that they are hard. So Yeah, so most of the woods are dark, and we just have a few flashlights pointing here and there. And mostly things appear to be hard, but we don't have the strong ability to say that they're hard definitively, but they just seem to be hard.
And sometimes the best evidence is just that, you know, many people have tried and we haven't come up with an algorithm. And sometimes that can be, you know, sort of convincing evidence along with these complexity theory arguments, because everything that we have in that area is somewhat indirect or indirectly related to the actual real world. You know, the evidence that we have for the kinds of circuits that we were just discussing typically, you know, relies on certain conjectures that are not proven but are plausible, and so, you know, at the end of the day, it's evidence, and I agree with Aram's point that these little miracles where we can simulate things are few and far between.
Actually, just to add, I want to add a little to David's answer. Computational complexity theory is the formal study of, among many other things, showing that things are hard to do on computers. But it's hard to prove things in this field. They rely on conjectures. And when we think about what makes something hard, it's tempting to turn to the field that has proofs and theorems, which is complexity theory. But at a certain point, we also need to make a sociological argument along the lines of what David said. And there, our confidence in the hardness of something grows with the number of maybe the number of years and people and resources devoted to solving it. So quantum mechanics has been of something of great interest to simulate since the 1930s. There are companies that spend hundreds of millions of dollars on simulating it. And, you know, you can look at what people have achieved in simulating quantum mechanics, and we've made good progress, but it still looks like a limited number of cases that can all sort of fit into some fairly simple templates. Factoring numbers is something that people have tried to do for thousands of years. The NSA has probably hired a large fraction of all mathematicians to devote to this problem. You know, and if we haven't managed to solve it, that gives us some confidence that it's hard. But, you know, you have to resort to these sort of sociological arguments. And one thing that complexity theory gives us is more people than we thought were working on NP-complete problems, because they all turned out to be equivalent and people were approaching it from different fields. But, you know, in the end, we're not going to have like a single theorem that does it. Like the sociological and the theorems will have to go together, I think, in reasoning about things being hard.
I see. So, okay, interesting. So, if suppose you find a circuit that you like particularly, right? And how would you go about convincing other people that this is actually a hard circuit, or what kind of methods do you have essentially to actually show that or convince people that that this is indeed a hard circuit as opposed to something that you could do easily, right?
Well, maybe I can. Yeah, maybe I can address that. So actually, one of the questions in the chat also addresses one of these methods, which is the the notion of quantum query complexity and establishing a speed up relative to what we would call an oracle. So there is a kind of a set of or a way to establish a speed up in a setting where part of the circuit, you're only given the input-output behavior of that part of the circuit. So if you imagine like, searching for a marked item, but the database that you have is only has input-output behavior specified. So you can ask it, is this the marked item? Is it number 5 out of 100, or is it number 7? And every time it just tells you, no, it isn't, or yes, it is. So that, you have this kind of input-output behavior. And that's, you can call this oracle, which tells you whether or not a given item is marked, and we know, that in the classical case you need number of oracle calls, which is roughly the number of items in the database to find the marked one. If there's only one that's marked, you have to search for a linear number of calls. And in the quantum case, we have Grover's algorithm, which gives you if you had 100 items in the database, you only have to make roughly 10 calls, or the square root of the number of items. So that's a setting where we can prove that there's a speed up, but only in the situation where we have this like kind of artificial setting where part of the part of the task is to interrogate this oracle that's given to you as a black box. And in the real world, the problems that we have don't have that, black box structure. They actually are given in a more detailed way. But nevertheless, it gives us some evidence that, if you only consider algorithms that don't use the structure of your database, say, or don't use the structure of your problem, then we can really prove that there are speedups. So that's one setting where you can sort of know, in a certain sense, that quantum algorithms can be more powerful.
Yeah, I guess
yeah,
I have to go in a minute, so let me just add on briefly, disappear, and then hopefully come back. What David's saying is an example of something more general, which is we often can prove something. You often cannot prove that the specific thing you want is hard, but you can prove that something hopefully nearby is, and then you can reason why they may be similar. So an oracle is one example. An oracle argument says, look, here's a subroutine, and I believe that by inspecting the code of that subroutine, I can't do anything better than just running it. That's one way of explaining it. Of course, another one, I guess, to answer a question about the Hastings adiabatic evolution paper, which looks amazing, is you also need to be able to believe that you can come up with obfuscated code for this oracle. So sometimes when we see an oracle result, we don't actually know code that would instantiate it. Another way you can reason that things are hard is often we can show that the worst case version of a problem is hard. And then what we actually want is we want to hope that the average case version is hard. For example, for cryptography, it's important that factoring is hard, not only in the worst case, but on average. It has to be that when I generate an RSA key and I choose those primes at random, that their product is hard to factor. Not just that there exist two primes out there that are hard to factor. This has to be an average case hard problem. And for a lot of these things, we might have pretty strong evidence from complexity theory in that, it relates to something that's been widely studied by a lot of people and no progress has been made, and it's equivalent to a lot of other problems, that something is hard in the worst case. And then we have pretty thin evidence about the average case version of it. But we have to make that kind of speculative leap there. So sometimes that is one of the ways that we reason that things are hard. Now, I apologize, our babysitter is leaving. If one kid successfully naps quickly, you will see me again soon. If not,
Yes.
I will leave you in David and Kristan's capable hands. Thanks, everyone.
Good luck. See you soon.
Good luck. I hope to see you soon if it works.
Maybe I could also just follow up on this discussion, because I think it's an important point. And one thing we haven't discussed is the arguments from post-selection, which I think are really kind of wacky, but also like kind of amazing that they work. So these arguments go back to Aronson and Terhal and DiVincenzo, and sort of run through this whole area of restricted quantum computations and their power. And the amazing fact that turns out to be useful, but which you would never think was useful, is the following thing: that if you have a quantum circuit, and imagine a situation, which is not the real world, but imagine a situation where you can run the quantum circuit, measure the first qubit, and then post-select on the output being 0. So you only ever, you imagine a situation where you run the circuit, and then every time you measure this qubit, it's 0. So you only ever get the output when this qubit is 0, and that sort of post-selection is done for you in one time step. So if you imagine that type of quantum computer, which obviously does not exist in the real world because we cannot post-select. In the real world, we would have to just run it many times until we get 0. But imagine that work is done for you by some all-powerful being. That the power of that post-selected quantum computation is vastly more than the power of post-selected classical computation. So in complexity theory, you would say that the post-selected quantum computation is outside of the polynomial, can solve problems outside of the polynomial hierarchy, and that fact really limits the classical simulation of quantum computers in the real world. Because if you had a classical simulation of a quantum computer in the real world, imagine you have a classical simulator. Now you can just post-select the classical simulator, and you get a post-selected classical computation that simulates a post-selected quantum computation. But I just said that the post-selected quantum computation is much more powerful than post-selected classical computation. So that argument, as wacky as it is, has led to this whole notion of quantum computational supremacy and so on, and the arguments for why sampling from the output of a quantum computer is hard for classical computers.
So briefly, before, could you give a brief definition for folks what post-selection actually means if they're not familiar with that? I mean, you alluded to that, you told that at the beginning, but maybe in a small definition for people that are not familiar with the term.
Yes, so imagine that you have n qubits, and you run a quantum computation, and then you measure the first qubit, and that measurement outcome is going to be random, and then you measure the rest of the qubits. But let's say you only care about the rest of the qubits in the case where the first measurement gives you a 0. Okay, so that could happen with very small probability, right? So you might have to run the circuit many times to just get one output that you care about. But in the post-selected model, you just get that every time you run it. You get only the ones that you care about, the ones that are post-selected on this qubit being measured in the 0 state. So in the post-selected model, you don't have to just run it many times. You run it once and you get and of course it's not a model that lines up with the real world. In the real world, we would have to run it many times and wait until we get this qubit being 0, and then we would get the output that we care about. So the post-selected model is not a realistic model of quantum computing, but the power of these arguments relies on the fact that post-selected quantum computers are for some reason much more powerful than post-selected classical computers. And if you had a simulator, you could get a post-selected classical simulator of post-selected quantum computation, which shouldn't happen.
See, so a brief follow-up. So I mean, what I recall is a lot of this post-selection argument hinges also on the fact that how strongly or how weakly you're able, on the classical end, what you expect that a classical quantum computer versus what a quantum computer do. So for instance, there's different kinds of errors we tolerate in one setting, the other setting. Could you briefly tell us a bit about, say, to which extent basically that matters? These kinds of errors would matter in such an argument?
Oh yes, yeah. So that is really an important issue, because the argument that I just outlined, which that argument really relies on the simulation being exact. So we have very, very strong evidence that you cannot exactly classically simulate sampling from the output of a quantum computation. So like if you had a classical simulator, you give it a quantum circuit and it samples bit strings from the output of the quantum circuit, that should not be allowed if the sampling really does the exact job of sampling from the output distribution. So there we have very strong evidence, but this goes back to Aram's point that all the evidence is kind of indirect, and we kind of build up a picture of what we think is hard based on attacking it from many different angles. So in the real world, of course, even the quantum computer cannot produce an exact sample because there will be error. And so then you throw that back to the complexity theorists and you say, well, you've asked the classical computer to do too much by exactly sampling the quantum computer. So now why don't we ask it to do something more reasonable and just produce a sample from a distribution that is close to the one that the ideal quantum circuit would produce. And so it sounds like a small change, but in the complexity theoretic arguments, it requires now for the evidence to be weakened a little bit. So there is now an additional conjecture which is needed about average case hardness of certain counting problems. And so in other words, we don't have as strong evidence for that task, for approximately sampling from the output distribution, but there is evidence. And again, it sort of goes back to this sociological point, which is that how do you process this indirect evidence, and at what point do you believe that it's really hard? Because in complexity theory, as I pointed out, we just we don't have the tools to really prove the strongest statements that we could imagine.
I see. Interesting. So you're right. So what we've been talking about mostly basically fits firmly into providing theoretical support for hardness arguments, right? So where you say, well, you have some reasons, you can manufacture a reasonable argument that basically leads you to believe that you wouldn't be able to achieve a given computational class easily in some other setting. So, but what if, say you want to experimentally go and verify something like that? So if you want to go and you want to verify that you did something that is hard, and convince someone else that you did something that is hard. What do you think, like in a practical setting, what are the challenges there, and what are the ways how you'd go about convincing someone that what you just ran as an experiment is a difficult thing to do?
Yeah, so I think the intersection of verification and practicality is the challenge. I mean, you know, if we were to run Shor's algorithm on a large factoring instance, then, you know, that problem can be verified easily because, you know, you want to factor a large number, you get the factors, and then to check, you just multiply them together. So, you know, of course, there are problems of that nature where we, you know, a large enough universal fault-tolerant quantum computer could solve them, and where we could check the solutions easily. But then, you know, that goes to your other point about practicality. So, you know, in the near term, we don't have large universal fault-tolerant quantum computers. And so, you know, then we could ask about these verification of these, you know, hard quantum circuits based on restricted models like constant depth circuits, IQP circuits, QAOA circuits, and so on. And the verification there is, I would say, not as strong. I mean, so you know, Google has proposed this linear cross entropy score as some kind of verification of their experiment, and that is being studied by many people. I mean, it's sort of, you know, I would say that we don't have as strong methods of verification for these near-term devices, and part of that is just because you know, the strongest evidence that we have for quantum computers being more powerful than classical computers really pertains to the universal fault-tolerant devices of the future, and so in these limited scenarios with restricted models, especially when you're asking to do something that we don't think can be done in the polynomial hierarchy classically, you know, the strength of the verification evidence is weaker, but it's again being probed very. You know, the theory community is certainly working hard on understanding these the verification protocols that have been proposed. So, for example, in the case of linear cross entropy, you know, there's been follow-up work by Scott Aronson and Sam Gunn, which shows that if you could classically achieve a high score on this benchmark that was proposed, then that would give you the power to solve some other problem, which you know, which we don't know how to do. But then, you know, there's also evidence in the other direction. I mean, especially when you combine many of these restrictions. So, for example, let's say you combine the restrictions of two-dimensional circuits, which are, you know, corresponds to the architecture that many groups are using, and random circuits, and constant depth. So if you combine all of those things, each of which individually, you know, is a powerful family of circuits, but when you combine all of them, there's sort of evidence that it may be classically simulable. So, so there has been some interesting work in that area. In fact, by Aram, maybe when he comes back, he can tell us about it, and by other people very recently on specifically spoofing the cross entropy benchmarking for such circuits.
See, interesting. So maybe we're at 42 minutes. So maybe one question in the end. So since we're all, I mean, in the end, I mean, here we talked mostly about the theoretical aspect of hardness and so forth. But could you immediately say, or could you say that basically, I don't know, what if you're a person that develops quantum algorithms, right? So why would you care about hardness results at all? Or why is there some practical relevance to basically caring about developing algorithms, or even going further? So further out, if you care about whatever the application is of the algorithm, why would you, as a person that thinks about algorithm, what would you tell those people where you say, well, why is it relevant that you actually think about hardness? Or maybe you could tell them, well, don't bother, it's going to be fine. So what is actually, why would you say this would be relevant or would not be relevant? Could you explain that a bit?
Yeah, I mean, I think your question points to the fact that, you know, maybe for now, because the devices are small and limited, you know, maybe there's sort of a, you either choose to do something hard or you choose to do something useful, or, you know, it's sort of like a spectrum. Like there's things that we sort of really have stronger evidence that it's hard, but, you know, those things don't tend to be as useful as something where you could say, well, you know, we have an algorithm, it can be run on a quantum computer, we have very little evidence for hardness, but on the other hand, it gives an answer and we could use that answer to do some tasks. So for example, you know, there are cases like the quantum approximate optimization algorithm that was proposed by Party, Gutman, and Goldstone, where, you know, we have evidence that the circuit that is run is doing something hard. But then, you know, the algorithm really is intended to solve optimization problems. So at the end of the day, you get a bit string. The catch is that we don't have evidence that the bit strings that you get are themselves hard to produce. So in other words, you know, you might do just as well on the optimization problem using a classical algorithm, even though you used what we think is a hard quantum circuit. So I think in the near term, there is this kind of tension because we have such limitations on the devices. Ideally, we might like to run Shor's algorithm where we have great evidence for its hardness and, you know, it's sort of in a way useful. You know, I think there's sort of a danger in going too far in either direction, right? Because I think that if we spend all of our time running circuits that complexity theorists love, but never turn into anything useful, then, you know, I'm not sure how much longer we'll be, you know, we'll be building quantum computers. But on the other hand, if we just say, well, I can design an algorithm that does something, and, you know, I don't really know how to analyze it or show that it's doing anything better than classical computers, then I think we open ourselves up to the kind of dequantization that happened in the quantum machine learning field, for example, where, you know, algorithms were proposed, we didn't really know that it was hard classically, but it seemed like, you know, interesting things were happening and it might be useful. And then, you know, later we learned that those tasks could be performed with, you know, with only a polynomial slowdown by classical computers. So this sort of expected speed up or the conjectured speed up wasn't there.
Which is interesting because, yeah, I think you're talking about the recommender system paper, right? That was dequantized by time. Right? Right, exactly. And most of them, they basically had a couple of components that you usually find in difficult and challenging large quantum circuits. So, oh yeah, at some point there was some form of phase estimation involved. At some point there was something else involved. So it looked really like something that would be genuinely hard for a classical computer. But then the assumptions were such that it was actually attainable by a classical computer. Yeah. Was a bit bizarre. So
I guess the weird scenario is that you actually are running hard quantum circuits, like hard to simulate, but the end-to-end task that you're solving is easy, right? I mean, that's kind of the worst case scenario, right? Where you use a very challenging quantum computation to solve something that turns out to be easy. That would be bad.
So yeah, that is a very good reason of why you should care about hardness or having some supporting evidence that
But to be fair, I mean, the recommendation systems, you know, there is, we don't know that it, although it's clear that there's not an exponential speed up for quantum or classical, you know, there may be a polynomial speed up, and it's possible that will be an interesting and useful thing. So I don't mean to talk too negatively about that, except to give it as an example of something where we had not really very strong evidence for this exponential conjectured separation, and then in fact it turned out not to be true, despite the interesting algorithm and possibility of a polynomial speedup. And actually more broadly, I mean, maybe I can just say that maybe exponential speedups are not really the be all and end all, because it may be that a speedup from quadratic to linear could be the killer app for quantum computing. I mean, it really depends, I think, especially in the near term, on whether or not the algorithm is well suited to the types of architectures and error mitigation that is available in the actual devices. And so it could be that you find something useful which does something only slightly better than classical computers, but nevertheless, that if it's useful and can be run very easily on a quantum device, that might be interesting nevertheless.
Let's see. Maybe as a last question before we start taking some questions from the audience. So, in terms of, as you mentioned, various constraints of practical devices and so forth. Just to get back, so how relevant do you think are errors or basically noise in different forms to take into account when you talk about, say, a complexity of certain things of circuits? So you say, well, there's decoherence. Do you know whether there's any results where people have basically in the presence of noise, people can say something, that whether it's hard or not hard to simulate that noisy output of the device?
Yeah, absolutely. I mean, I think generally speaking, I mean, we've been talking about simulating quantum circuits in a sort of broad sense, but really it's much more fine-grained than that. And depending on the very precise question that you ask, or the simulation task itself, the answer can be vastly different. So for example, we talk about random quantum circuits. For random quantum circuits, we don't think that, or there's no classical simulation which runs in polynomial time and which can sample from a distribution that's close to the output distribution, say with respect to some measure of distance between probability distributions like the total variation distance. So that's hard. But on the other hand, if you do add noise, then asymptotically, so if you add a constant amount of noise after every gate, like a depolarizing channel, then in fact that task becomes easy. And then of course there's the, you could even ask the classical device to do something like we were talking about before, which is much more stringent, like to exactly sample from the distribution, and then that can be, there are cases where that exact sampling is easy, but then the sampling from the approximate distribution is hard. So an example of that is this case of random shallow 2D circuits, where the exact sampling task is hard, but sampling to within a given total, epsilon of total variation distance turns out to be easy by results of Aram and collaborators. So I think that the practical errors that you see in devices, those are very, really from a theorist's point of view, those are very large errors. And generally speaking, most things become easy to simulate under a large amount of error like that, asymptotically. But then you can also ask about very precise simulation tasks versus more reasonable simulation tasks. And the answer can change pretty vastly depending on the stringency of the task. Aram's back.
Aram is back. Oh, really? Okay, great. Then just in time for the for a few last questions. Sorry.
We have a special guest.
Say hello to them.
Hello.
Hey.
Much brighter.
Yeah, sorry, I was away for a bit. Any more questions I can field?
So I think we're sort of at the hour. Maybe you're right back in time to take some questions maybe from the audience.
Sounds good. Sounds good. Oh, I see there are a bunch of ones in the chat window here.
Right, exactly. So
have Have they been addressed?
Some of them, yes. We addressed explicitly the post-selection question that came earlier as a definition. David talked about random circuits briefly just now. Maybe you want to pick another question for yourself that you'd like to address, or I can pick one as you please.
Yeah. So you talked about post-selection randoms. I guess, randomness. I don't know if I'm saying the same thing as David, but random is tricky because I would say there's this sense that the easy circuits are like these sets that measure 0, and then the things that are near those are still kind of small, within the space of all circuits. And if we just avoid those, it should be hard. But we don't know what the right distribution is. And for constant depth circuits, I have a recent paper that argues that if the sort of the obvious distribution, just choosing the gates at random, may not be the hardest one. So random is very tricky because, it's like, what is a random? Yeah, what do you mean by random? When you say like a random number between 0 and 1, it's pretty obvious. But when you say sort of random within the space of all circuits, it's not always clear what the right measure is. And another question. Yeah, I don't know if we'll have a scalable quantum computer in the next 10 years. That seems like a challenge, but it's the sort of thing where things could go. It's possible that things will go faster than you think if we go via a modular architecture. That's my one sort of avenue for hope, is that it may be that once we get a good module, we can put together a lot of those. But the reason why it's hard to make like specific near-term predictions is that it seems like none of our current architectures are actually scalable. And so they might be easily modifiable to be scalable, or it might be a hard modification. And I don't know.
Well, what you mean is that we don't, we have not, or experimental groups have not incorporated error correction? Is that what you mean?
I mean that if you have a chain of ions, you can't keep making the chain longer.
Oh, I see.
And our current ion trap quantum computers are based on single chains. And so then if you want to get more of them, you need to incorporate some new technology like shuttling or something like coupling to photons, which is yet another, every piece of it has been demonstrated in isolation. But that's a big, that's what I mean by it's a different platform. It's a different, it's a different type of ion trap. Superconductors have other issues of putting a bunch of qubits on the same chip.
So in regards to this, there's actually a question by, which was asking, there was a question that asked basically whether there's in terms of complexity or hardness, whether this can be seen to be sort of dependent on actually what the platform is by itself, or would you say that this is something very universal?
Well, I think that certain choices of the architecture really matter, at least in the near term. In the long term, we know that the choices that are being made, if the goal is to build a universal fault-tolerant quantum computer, there are many different architectures that can lead to that, all of which the computers could all simulate each other. So in a sense, once the system size becomes large enough and we have some kind of error correction and fault tolerance, then we'll be in safe territory. But for now, for example, the 2D architecture, there are things we can simulate in a 2D architecture more efficiently than in a 3D architecture, for example. And so I think in the near term for the experiments that are being done, it really does matter what the architecture is, what kind of error mitigation is being done, and so on. That really has an interplay with the hardness of the tasks that are being performed.
Any last comments you guys would like to make? We're towards the end of the hour. Were you worn out?
Well, maybe I just want to thank everyone for joining. I've never done anything like this, and it was fun, and the time kind of flew by. So, yeah. And thank you, Kristan, for hosting.
Well, I would.
Yeah, I would say the same thing. Good.
Thank you, you guys, too. Thank you very much for taking the time, which is a very difficult point. I understand that you actually make time to be able to come here and join us and explain us things. I really appreciate and really enjoyed your explanations. That was really great. So thank you very much for coming on. And I'd also like to thank the viewers that actually managed to tune in and took their time and looked at this discussion. We really appreciate you being here. And I think with that, thank you very much. And I guess we're going to be checking out very soon. Thanks a lot. Bye-bye.
Bye.